Hi, my name is Nicole Knop, and I'm a chemistry major from the class of 2019, and with me is Jamie Zaletta, another chemistry major from the class of 2019. We'll be working through problem number 7 from chapter 5.2, Practice Problems in the General Chemistry Workbook. This problem is a calorimetry problem, provides a great example of solving techniques on what you should consider when solving a problem of this type. Here I have drawn a calorimeter, and this just gives a visual idea of what is taking place in this problem. Calorimetry is the process of measuring the amount of heat released and absorbed in a chemical reaction. The change in heat can determine whether or not the reaction is exothermic, which releases heat, or endothermic, which absorbs heat. A note to make is that the heat loss and gain in the reaction is conservative between the system and the surroundings. This idea can be connected to the equation Q system equals negative Q surroundings. The heat lost by the system is the heat gained by the surroundings, or vice versa. When we first start out with a calorimetry problem, a nice way to understand the total heat of the systems and the surroundings is to draw a heating curve. Here we have a heating curve for paraffin where the temperature is on the y-axis and time is on the x-axis. In the figure shown, we have 3 different partition slopes on the graph, and each corresponding to the phase of paraffin at different times of the reaction. We know that when the slope is flat, that the temperature is remaining constant, and we can use the equation Q equals N delta H. And that when the paraffin is not undergoing a phase transition, the equation to use is Q equals MC delta T. In this problem, we're looking from 65.6 degrees Celsius to 85 degrees Celsius. So we're just looking at this flat part and then this sloped part right here. For some students, it's hard to determine what is the system and what is the surroundings. And a good way to check yourself is to know what is of interest in the problem. Here in the problem, paraffin is of interest, so that is going to be the system and the surroundings is going to be the water. From the heating curve, we know that the paraffin is melting to become a liquid and then heating up in the liquid state until 85 degrees. To find the total heat gained by the paraffin, we need to add Q equals N delta H plus Q equals NC delta T. Then, once we know the total heat, we can solve for the specific heat capacity for the paraffin. The first step is to solve for the total energy loss from the surroundings, which in this case is water. We're going to be using Q equals MC delta T and plug in the information we know in order to get the total heat lost. I have given the information, which our starting volume is 61.8 milliliters. We have the density to convert the milliliters into grams. We know the specific heat is 4.184 joules per grams degree Celsius, and then we have the T initial and the T final. So I went ahead and I plugged in the information, and when you solve this, you're going to get Q equals negative 1,292.856 joules. Here I set up the equation Q system equals negative Q surroundings to show you how the heat lost by the H2O is the heat gained by the paraffin. We found that the heat lost by the H2O was a negative number, but when you plug it into the equation that has a negative in front of it, the negative times the negative is going to get you the positive. Here I've given the information from the problem that we can be using to plug into the equation Q equals N delta H plus MC delta T, and this is the total heat gained by the paraffin. I went ahead and I plugged in the information that we know, and from this we can see where the units cancel out and how we can determine the specific heat capacity of the paraffin. So usually whenever we see N delta H, we automatically think that N is going to be in moles. But in this case, because delta H diffusion has joules per gram, we're going to keep the N into grams, and so we can just think of this as an M if we wanted to. So we're going to have joules on this side and joules on this side, and then that equals to our joules overall. So go ahead and multiply yourself and see if you can come up with the specific heat capacity for the paraffin. You're solving for C in the equation, and when you do this, you should get that the specific heat capacity equals 2.50 joules per gram degree Celsius. If you did not get this answer, maybe check your units again and see if you did the right multiplication and division. I hope this video has helped you understand calorimetry a little bit more and can help you further in 128.